clicker. Yeah, okay. Well, it's good to be here this morning, and it's the first time I've actually been to the Moose, so nice to see that this association is so large. You guys are interested in the lake. That's great. We're going to do something a little bit different here. Of course, we're going to start to step back in time. I'm going to bring you forward Dan, who is my lab assistant and my graduate student who's working on his PhD, is passing around a geologic time column. I figured it would be nice just so you had a reference in front of you, because I'm going to be throwing out some dates and ages, and if you haven't had any kind of formal geology, it might be a little confusing, and I don't want to do that. So, but I do want to take us through a little trip through time here and show you how varied the life and geology of this area is. I mean, it's truly mind-boggling when you take a look at it going back. So, what's that? Okay, can you hear me better now? Yeah. Okay, good. Okay, so the geologic history of our area, and I mean Ohio in particular, but definitely our area, is really rich and varied. In our counties, if we go to the quarries and river valleys, we get into the Silurian period, which is over 400 million years old, okay? And then as we come back up into the soil, into the actual land that we walk on, a lot of that is Pleistocene in age from the ice ages. So we have a 400 million year gap here, but I'm going to try to fill in some of that gap. If you go to the south, and if when you drive down to Dayton or Cincinnati and you look on the sides of the road, you'll see very large road cuts. That is late Ordovician in age, about 450 million years old. And the fossils and sediments are so well preserved that it brings people from all over the world, not only to do research, but also to collect, okay? If you go to the north, up in Van Wert and Paulding counties, we get into incredible Middle Devonian strata and fossils. Again, places where people will come from all over just to collect the fossils. And it's just amazing preservation, okay? So you all probably know this, in our fields and streams, riverbanks, you can find Pleistocene mammal remains. It's probably about every few months somebody has a picture of something they found and want to know if it was Bessie the cow or was it a mammoth or something like that. So sometimes it is Bessie and sometimes it is actually a mammoth or a mastodon. So, and I think this is a really interesting thing, because the Grand Lake area was once the most productive and richest oil and gas field in the world. It didn't last for long, but for about 20 years, we produced most of the natural gas and oil that fed our kind of industrial revolution. So, interesting. Well, being a professor, I have to give you a few little lessons, right? But I'll make them as easy as I can, okay? Just because we're going to talk about things moving around. And so an understanding of the Earth is pretty good. I think most people realize we have a core and a mantle and crust. And this is a simplified view, but the core, the inner and outer core, are very hot. And especially the outer core, it causes convection and conduction and movement of the mantle itself, which then moves the crust around. And the crust is fractured into plates. We call them tectonic plates. And every time you hear about earthquakes or volcanoes, we're usually talking about the interaction of these plates. So the Earth is very, very dynamic. And part of that reason is because the Earth is really a water planet. And the water actually aids the tectonics, okay? I like to show this slide to say, what is a continent, right? Well, our continent has a few of these things called cratons, okay? And these are the primitive crust of the Earth, the really old stuff, the stuff going back sometimes 3 to 4 billion years old. And that's the core of our continent. But, if we're like in Africa or South America, there could be 3 cratons altogether. Those things have come together to make what we call the present day continents, like South America, Asia, North America. So we live smack dab in the craton right here, okay? We're actually on the continental platform. That's where the sediments collect. So our sediments are at least 1,000 feet thick or more before you would ever hit that hard rock. Now, if we would go up to Wisconsin, Michigan, Minnesota, we could actually see the continental shield. That ancient part is exposed, okay? So we're in the solid part of the continent here, okay? But to the east and to the west, especially to the coast, we get into the parts that interact with the tectonic plates, and that's where we see primarily our mountain building, and then past the mountains we get into the coastal plains, and then the continental shelf and then the ocean. Now we're on dry land right now, but this is not always the case. And you got to understand that, you know, this is not a constant thing. Eventually this continent will become part of another continent. But the thing that's interesting is the cratons tend to stay together. So one day North America won't look like it is, but this piece that we're on, which is huge, will just be a part of another landmass. Okay? I don't know how much about plate tectonics you've heard, but these plates interact with each other. Sometimes one goes below another, and this is called subduction, and this brings continents together. And when continents come together, they collide and form huge mountains. Also, as those plates dive down, they melt and throw up magma, which produces volcanoes. If we get out to the mid-ocean, we have an area where all around the Earth, it looks like the stitching of a baseball, the plates are actually spreading apart. And it's a good thing, because that's how plate tectonic works. But if you keep spreading, the Earth will get larger, which we know it does not, so we actually recycle that crust at the subduction zones. And so that's where we're going to see lots of volcanic activity, and we're also going to see a lot of earthquake origins. The third type of interaction is when the plates move side by side, okay? And these are called transform fault boundaries. A classic example is in California. The San Andreas is a system of faults where the North American plate is moving to the southeast and the southwest, and the Pacific plate is moving to the northeast. So one day, LA and San Francisco will be together. It won't be good, but they'll be together, okay? Now, a little bit about geologic time. Hopefully everybody's got a chart in front of them. MA means millions of years ago. GA means billions of years ago. But here's the cool thing. If we take a look at those things called eras, Ohio has most of the Paleozoic era exposed in rocks, except for the Cambrian, which is at the very bottom, and just a teeny tiny bit of Permian in the southeast. Okay, the rest of the state, if you go to different places, actually has those rocks of those ages exposed. Now, the rocks under our feet, again, are Silurian, so that gives you kind of an estimate of around 420 million years old. And then there's a vast jump into what we get into the Pleistocene epoch, which is the ice ages. Okay, so everybody says, well, where are the dinosaurs? Well, dinosaurs did walk around in Ohio, but they didn't leave their fossils behind because Ohio at that point was above sea level. And any rivers or sediments that were collected that could have fossilized those things have been either filled in by glacial sediments or wiped away by erosion. So we don't get, if you want to consider that exciting, we don't get that. I don't consider the dinosaurs as exciting as some of the gigantic fish that actually lived in Ohio. So I think that's pretty cool. For example, Cleveland area has some of the best known earliest fish, sharks, placoderms. It's incredible preservation, right? So we'll just kind of touch on that a little bit. But so everybody sees that, you know, geologic time, we start at 4.5 billion years ago, go to the present, we divide it up into pieces for reference. Those are not arbitrary pieces. Those are actually based on erosional boundaries typically. And by that I mean big events where sometimes the oceans rise and flood the cratons. And so there's been at least 3 times where Ohio's been underwater, all right? So if we're going to begin our journey, we got to go back not 200 million years, not 12,000, not even 400 million, but 1.2 billion years ago. And around that time, let's see, does this laser work? Yeah. Around that time, this is most of what we call that craton, that North American craton we call Laurentia. Each of these different color pieces was a protocontinent that got sutured together to form our craton. So piece by piece, it built up North America. And if you notice, there's something kind of interesting right here. You see this thing that says 1.1? That's 1.1 billion years ago. The North American continent started to fracture into pieces and would have continued to fracture, except for there was another protocontinent to the east that came and slammed into North America and sealed it all up. And that is called the Grenville Province. And why do I bring this up? Because you can see, first off, the Grenville Province forms the east coast of North America. Secondly, we're standing on the edge of the Grenville Province right now. So we have a suture line between the primitive North America and the Grenville Province that came together, sealed up North America, and finished building what we know today as North America. Now, because that is a suture line, it's like a scar, okay? You know, if you have a scar and it heals, everything's cool until you bump it, and then it hurts again, right? So that scar never totally heals. And so we're right on that boundary, and this gives us our seismic activity that we have in this area, okay? So you know that if we look at in last 200 years, 150 years, there's been a fair number of earthquakes in Ohio. I mean, nothing above a 6, but some in the 5 range on the Richter scale. And you got to remember, every time you bump up one number, that's 10 times stronger. So if you go from a 4 to a 5, that means that earthquake is 10 times stronger. And notice that we have some really biggies up there near Cleveland and right around here, right here smack dab where we live. And that's that Grenville fault, front line. And here you can actually see where the front is. So this is the old part of North America, and this is the younger part of North America. And we're right on that edge. Of course, every once in a while we get some pretty decent earthquakes. This is from the 1937 Anna earthquake, which literally brought some buildings down, destroyed the insides of houses, cracked chimneys, really caused a lot of damage. I don't think we've had anything quite that strong since then, but we've had some 4s, some 4.5s. Now, thing is, our suture line, right, is actually attached to other suture lines. So have anybody ever heard of the New Madrid fault? And that's in Missouri, right? On the border of Missouri, Kentucky, and Tennessee, kind of like that weird little bubble all the way down there. That thing is very, very active. If you go to the USGS and look at earthquakes by the day, you'll see there's always activity around the New Madrid. In the early 1800s, it let loose to almost a magnitude 10, which is one of the largest we've ever known. Now, there wasn't much built up in the Midwest at that time, because this is around 1810, 1811. But eyewitness reports actually say that cattle were thrown in the air by the waves that went across the land. It was so powerful an earthquake that church bells in New England and Canada were ringing. Now, if that ever goes off, that's going to actually trigger our Grenville front fault. So that's something that, you know, we'd probably get a decent sized earthquake then. So, but not to scare anybody. I doubt it'll happen. Probably happen eventually. I mean, you can't build mountains without earthquakes. I mean, that's the thing, right? Just to show, too, that if we take a look over the last 550 million years in North America, there have been at least 6 times where sea levels have risen and covered the center of the continent. For Ohio, that's happened 3 times. And we give these things names where the sediments are really indicative of the sea level rise. And we'll take a look at that in a minute. Notice that the sea levels are particularly high here from around 550 to around 300 million years ago, and then the sea levels fall for quite a while. That's during the time of the great supercontinent called Pangaea. So as the continents start to break up and move, that actually causes rifting in the ocean floor, and that rifting causes the ocean floor to buckle upwards and makes the water spill onto the land. Then as the continents stop moving rapidly, the sea levels come back down. Now, there's been a super cycle like you see there, but there's also been other cycles on top of it. So here you can see that this thing called the Tippecanoe sequence, the Kaskaskia and the Absaroka, these are all parts of the times that Ohio was underwater. Okay? So at least 3 times during that Paleozoic. One other thing to keep in mind is that as continents collide, as pieces come together, you have to think of it as like, okay, if a car is going 50 miles an hour, 60 miles an hour and slams into a wall, you get a lot of damage right in the front, right? But even the back now is warped, right? It's out of a line, the frame is twisted, and that's what happens to our continent. Every time there's one of these big collisions, pieces buckle or fold downward and give the continent kind of a dimpled appearance. Now, we happen to live on what's called the Cincinnati Arch. Literally, it's a topography that starts around Tennessee and goes like this, and then all the way down to Canada. So, at the top of the arch, sediments erode away much faster than they do at the bottom of the arch. So we live on the part where the sediments erode very quickly and expose the older stuff. That's why we have those really old fossils in the area. And this shows the tri-state area, and as you notice, see this light pink? This is the oldest sediments. And so right up around here is where we live. This purple is the Silurian. So that's what we would see if we could strip all the soil off, we'd be into the Silurian strata in our area. Notice as you go to the north and as you go to the south, the east and the west, the sediments become much younger. That's because they're not eroding away faster. We live on the arch, and the arch has provided us with an exposure into the past. All right, so let us start our little journey here. So this is the late Ordovician, around 450 million years ago. The circle is that tri-state area I showed you. We're right in that circle. Notice we're under the water. Okay? Got land to the east and north, a little tiny bit to the west, and there is no west coast of North America as we think of it today. If you wanted to imagine what did the seas look like, what did the life look like, here's a picture. It would have been dominated by these long-shelled nautiloids that sometimes got 20 feet long. So imagine an ice cream cone 20 feet long, about this big around, with the thing coming out of it looking kind of like a squid or an octopus with a beak about this big. And these guys would have been the terrors of the sea of the Ordovician. This is before you really get into the more advanced fishes. There are what we call the jawless fishes, which are about this big. They have bony coverings on the outside, but they don't actually have jaws. They have like a little ring for a mouth. Really primitive stuff. This is the time of invertebrates, okay? And so this leaves behind some of the best fossils in the world for that period of time, especially the trilobites, which, by the way, Isotylus gigas is our state fossil. And the actual Isotylus gigas down at, I think, Caesar's Creek is about this big. So really neat. But trilobites galore down that area, things called crinoids, which are related to starfish, beautiful critters once they're prepped out of the sediments. Just amazing diversity of life and things that we don't see today. Horn corals, people find those and always ask me, is this a dinosaur tooth? No, that's a coral. It's just like an ice cream cone coral, if you want to think of it that way. Brachiopods, which a lot of you don't know what it is, or maybe you've collected some of that stuff. That's very common. Not so common are clams and mussels and things like that. Some of those bivalve mollusks exist, but brachiopods, which are much more worm-like on the inside, were dominant during the Paleozoic. Now we get into the Silurian. Notice where we are. We're 30 degrees below the equator. Notice how this piece here, this is going to actually suture itself up to the rest of North America and start building the Appalachian Mountains. Okay? We're going to get a lot of those sediments that are going to be shed eventually to this area. So, what did the Silurian seas look like? Again, lots of invertebrates, but this time we have these giant sea scorpions called eurypterids. Some of these are 6 to 10 feet long. So imagine a sea scorpion. They call it a sea scorpion. It's not quite a scorpion, but it kind of looks like one. Imagine going to your basement and seeing a 3-footer of one of those, right? I mean, you know, you'd have to get some pretty big boots out to stomp on that thing. That was probably the apex predator of the day, okay? But you notice that we are starting to get more fish varieties, okay? So the jawed fish are now around. The first chondrichthyans, sharks and their relatives, come about. Probably even going back to the very early Silurian. And the first relatives of the tetrapods, the four-legged things that we see today, the vertebrates, those relatives are starting to come around as well as the regular bony fish. Again, fossil-wise, beautiful fossils. Good trilobite varieties, really weird echinoderms. I mean, these things all had stalks on them and had little arms that came out of the top, and they filter fed. Okay? Unfortunately, and I'll get to this, in our area, we're never going to see that type of preservation. If we go into Indiana and down into Kentucky, we will see that kind of preservation. But it has to do with, and I'll get into this, what the seas were like during the Silurian in this area. And again, just to show you some more of the variety, these are the crinoids, very sought after by collectors, going for sometimes tens of thousands of dollars. Okay? And again, our brachiopods. And this snail is pretty interesting. Every time we find that snail, it's usually on top of one of these crinoids. And actually, it, how can I put it? It's a poop eater. Okay, so that's its niche. It sits on top and it takes the waste from the crinoid, and that's how it lived. So nothing goes to waste in nature. Sure. Okay, now we get into the late Devonian. Notice where we are now. We're above 30 degrees, and notice that the seas are starting to shrink back. The Appalachians are starting to build. Look what's coming up from the south, though. Okay, this is going to be Africa, and parts of South America are going to collide with what we call Laurentia or Laurasia eventually. This is our part of North America. We're kind of connected to Asia. And so these two big pieces are going to come together. Sometimes the Devonian is called the age of fishes because at this point, there are so many different weird types of fish, stuff that's extinct today, okay? Things that you can't even imagine. What I'm calling sharks are really chondrichthyans. They've got big spines coming out, brush complexes, whorls of teeth coming out of their mouth, right? The placoderms, they're still around, Dunkleosteus and some of those really gigantic, big-headed fish that look like guillotine mouthpieces, right? Just bizarre stuff. I know someone once told me, imagine you're in a boat fishing in the Lake Devonian. Every time you caught something, you'd scream like bloody murder because it'd be so scary, right? But by the time you get into the Mississippi in the next period, you'd go like, yeah, it's weird looking, but I recognize that. You wouldn't be like at the end of the boat screaming or anything like that. So this is a weird time. Again, nice trilobites. These all come from the Silica Shale up in Paulding County. Okay, has anybody ever hunted the Silica Shale in Paulding County or north into Toledo? They have parks that you can go into, and occasionally the quarries will let you in. So they used to let you in a lot more, but yeah, because of liability and everything, they're kind of sticky on that. Again, we have our crinoids. And what's really neat is some of these brachiopods are about this big, and they've been turned to pyrite. So they're kind of golden in color. This is Dunkleosteus. This was found around the Cleveland area. This thing's about 10 to 15 feet long. It's covered in those hard bones. Notice that the mouth is kind of like a guillotine. So this would have been swimming in those seas. But it wouldn't have been as flexible as, say, the early relatives of the sharks or the bony fish. Okay, this is actually one of the very primitive sharks that was found in Cleveland. In fact, we prepped one of those out in my lab and wrote a paper that went out several years ago about that and kind of dispelled some of the myths about those early shark-like things. So Cleveland has one of the best assortments of those Devonian fishes. Bet you guys didn't know that, right? So our state has some of the best fossils in the world. All right, so that's pretty cool. Now we get into what's called the Mississippian. The Mississippian, and above it is the Pennsylvanian. In Europe, they call it the Carboniferous because at this point, there's huge swamps all over the place. Okay, sea levels are high, but they come and they recede. They come and they recede because at that point, the Earth is in one of its ice ages. And so as the ice grows, the sea levels drop, and these swamps grow, these huge swamps. And then those swamps die, they grow, they die, and they lay all the stuff that becomes peat and eventually coal, okay? So you can see at this point, we're still underwater, but there's the mountains. And so sometimes, even though our portion of Ohio is underwater, the eastern portion was not. Okay, I think you can see that the fish are starting to look a little bit more familiar. This is a shark, Chondrichthyon. Shark is a colloquial term, unfortunately. But yeah, and that is too. And there's a bony fish, and there's some bony fish. And they kind of look like something we'd see today. I mean, we wouldn't be screaming, like I told you, so. Fossils, you really have to go to the mid of the state to get to the Mississippian fossils in Ohio, but we do have some decent fossils up around, like from Columbus north, getting toward the Appalachian Plateau are good areas to actually collect. Now we're in the Pennsylvanian, and notice now we are above sea level. And again, now this is a time of swamps again to the east. All right, our portion of Ohio doesn't really have any sediments from the Pennsylvanian, but all we have to do is go northwest and we can get into them again, into the coal fields. And so what did those seas look like? Well, the seas were, again, interesting. Still a lot of invertebrates, but notice all the types of sharks and fishes. And what's really interesting is if we go out east to around like the Athens area, the Pennsylvanian is really well exposed. And that was a real swampy area. So you can actually get into spots where you can find sharks that lived in like these restricted little ponds and lakes. But you can also find the remains of cockroaches about this big and dragonflies with wings like that, and really cool looking swampy plants. And that's all exposed all on the eastern part of Ohio. So just to show you, this is some of the fossils that you'll find in Ohio in the Pennsylvanian. That is a shark tooth called Petilotus. This is the root. That's the part that comes above the mouth. And this is an embolomere, a big amphibian about this big. And so now we actually got things that are walking on land that are vertebrates. Notice all the little teeth. Actually kind of a nasty little guy. I found a jaw of one in some of the limestones out in eastern Ohio that's really not supposed to be there, so that's going to be a paper. So that's pretty cool. Unfortunately, a lot of work hasn't been focused on Ohio in the last, say, 50 or so years. Everybody's interested in going to South America, Africa, and Asia, but it leaves everything here undocumented, and we need plenty of workers in North America to actually uncover the geologic past. One of the things you will find, too, are incredible plant preservation, and these are all Pennsylvanian plants. These are non-flowering plants. Flowers are not going to come around for a long, long time after this. So, and then finally we get into the early Permian, and you can barely see that little circle, but the Appalachians are fully built now. This is Africa. This is North America. Up here is Asia. Down here is South America. And only in the very eastern part of Ohio, which was swampy enough to preserve fossil remains, is where we actually have some fossils from the Permian. Okay, so at that point we have these mammal-like reptiles like Dimetrodon that are living in the area. We have these bizarre-looking sharks that are living in lakes. And how do we know that? Because we have tracks and trails of those mammal-like reptiles. We actually have fossil remains. And of course we have plants. All right, that's an overview of our state through time. Sorry it took so long, but hopefully it was kind of interesting. Now, back to the Silurian of west central Ohio. Notice that in North America, these are the only Silurian outcrops. And where's the biggest one? Indiana and Ohio. And what's really interesting about this is here you can see all the Silurian strata surrounding us in the lake, right? These became big restricted seas. You got to imagine these reefs that formed around this area would be like the Great Barrier Reefs. And these seas would be disconnected from the other ocean. And over time, these seas would get saltier and saltier. And eventually, the minerals would start to work their way into the limestone and turn the limestone into what we call dolostone or dolomite. So where we live in Ohio, everything is dolomitic in the Silurian. And I mean, we mine this stuff all the time. There are quarries everywhere, okay? Why do we mine it? Well, first, it can be produced into aggregate for concrete. Secondly, it can be dimensional stone for building. It's very pretty, some of it, when you slice it. There's primarily the reason. Sometimes you're actually going to clear some of the Silurian out of the way to get a little bit deeper, but that's not that usual. But a lot of times it's also used for road fill and driveways, and if you have a stone driveway with the like whitish gray stone, that's dolomite. And dolomite reacts with acid, but very slowly, so the stuff lasts forever, right? So good building stone. So here's the system of reefs that are existing here in Indiana and Ohio. So this is a restricted area and an evaporite basin. And a lot of people don't realize this, but underneath Michigan, particularly around that southern part, like Detroit and all, is a huge salt dome, okay, from this evaporating seas that left their salts behind. The salt dome is so big that, I mean, imagine having a Tupperware bowl about this big, right? And then a little pencil eraser sitting on the top. That'd be Detroit, and that'd be the salt dome. That's how big it is. And a lot of the salt that we use comes from that area. So this is all from those restricted seas and reefs that formed during the Silurian. Now, these are our particular fossils from the area. Notice that they don't have the outer covering like we saw before. That's because as the limestone turned to dolomite, the very outer part of the fossil is lost. But the actual shape of the fossil, the exterior of the fossil, is very well preserved in the rock. So when you hit the rock and you break it open, sometimes a natural cast will pop on out. And other times you can take what's left, what we call the mold, and for us, these are actually plates from a paper we just published last year. You can pour silicone in there, pop it out, and you've got a complete replica of what the fossil looked like. So we've got an incredible diversity of invertebrates here, but a lot of people are like, it's all dolomite, who wants that? Well, actually, they're very pretty, and they're scientifically very important, and we got a really large paper out of it. So that was Ohio State and Wright State Lake put out a paper finally. I've been here almost 23 years and swore we were going to get one out, so we finally did. I'm not just a shark worker, primarily, but anything interesting I'll work on, so it doesn't matter. Okay, where do you see this Silurian stuff? Well, this is Poppelman's Quarry on the border of Dark and Miami counties. This is a very vast tract of Silurian. But you don't have to go down there to see it. You can go to Stone Cove up the road, and you can see the reefs there too. That is Stone Cove, and here you can actually see those color bands. That's part of the reef that formed during the Silurian. And a lot of those fossils that you see came out of both of these quarries that I showed you before. Okay. Any questions so far? I say that to my class. I look, and sometimes I have to make sure they're all still breathing.
Why don't we find more gold why don't we have the gold, have gold like in our...
You need to have the hard rock for gold, the igneous and metamorphic rock. We're really more into the sedimentary rocks here. Yeah, it's the type of rock that doesn't usually accumulate the metals and stuff. Although sometimes, and I'll show you, the glaciers brought down rocks from that craton area that's exposed at the top, and that's pretty cool. All right, so let's move ahead 400 million years. See, we have to zoom ahead here. This is crazy. But you know how we say we're living in a time of a warming climate? And you hear, I don't want to be controversial, but you hear people saying, like, it's the warmest temperature ever was recorded last summer. You don't know where they get that from. If we go back into the Eocene, this is about 50 million years ago, the Earth is in one of its hottest times ever. I doubt that there's any ice anywhere on Earth. I mean, it's so hot that in England, it has an African fauna. There are crocodiles living in Montana. All right, it's hot. And we get to this maximum, and then very quickly, the Earth starts to cool again. So the Earth has gone through many ice ages in its history. We know about 3 periods, what we call them ice houses, and we're in one now. And you notice that around 40 or so million years ago, the temperatures start to really fall and then continue to drop until we get to where we are today. So today we're actually in a pretty cold regime. Why did that happen? Well, around 50 to 40 million years ago, this piece of land we call India was coming up from where Australia is today and collided with Asia. And it's continuing to collide. In fact, India is actually going underneath Asia, and that collision has brought up the Himalayas. And so those mountains continue to rise, and north of those mountains is the Tibetan Plateau, and this is a very, very big region of elevation. And as those rocks go up, they erode very quickly. And as rocks erode quickly, and here we're talking about the hard rocks, the igneous rocks like granites and things, it pulls the carbon dioxide right out of the air. And so it combines with that and actually forms limestones in the sea. So what's been going on as those mountains have been rising, the CO2 levels have been dropping, and the earth has been cooling. No matter what we do today, in 2 million years, this earth is going to be back into a big time glaciation ice age, no matter what we do. And I'm a historical geologist, so we don't look at 1,000 years, we don't look at 10,000 years, we look at 100,000 years, million years. Climate is always changing. It's never stable, okay? We'd like to think it is, but it's never stable. So right now we're living in a time of a little bit of climate change. Part of that is natural, part of it is probably man-made. It's hard to divorce the pieces together. And what's going to happen is anybody's guess. So over the last 500,000 years, you can see we've had cold, warm, cold, warm, cold, warm. Every time it's cold, we have glaciers building. Every time it's warm, the glaciers melt back. Right now, we're past that glacial stage. We're getting past that glacial stage. So the glaciers are actually starting to melt back. We're in, a post-glacial part of the ice age. We're still in the ice age, but we're in a post-glacial part of the ice age, which could start glaciating at any time. It doesn't take much to trigger this, okay? Here, I'm actually showing you carbon dioxide laid on top of the temperature variation. Notice when carbon dioxide levels are high, temperatures are high. When carbon dioxide levels fall, temperatures fall. But every time the carbon dioxide peaks, it falls rapidly. There's where we are right now. So we're due for a fall. Now, we may have been going into that fall way back during the Little Ice Age. And then the Industrial Revolution came around and started putting carbon dioxide into the air. Maybe we've prevented the glaciers from covering Ohio and North America. I don't know. It's an interesting thing. All right, a little bit about glaciers, right? We all talk about glaciers. What is a glacier? Where do they form? They have to form on land. They do not form on water. Okay, when you get ice on water, that's sea ice. As the glacier moves off the land and into the water, it calves. It breaks off pieces, and these are called icebergs. In any glacier, there's a part where the glacier is accumulating and a part where it's melting back. And if everything is in equilibrium, this front here will stay stationary. But even if it stays stationary, the ice is continually moving down below, grinding away the land and bringing all that rock and stuff right to the very front. And so if the glacier starts to melt back, all that rock and stuff remains, and the next front forms. And then that melts back, and that part remains. And you get a system of ridges. Okay? We call these eskers. And we call them moraines. And so there's all different types of moraines, and these moraines are the ground up rock from the glaciers moving. There are what we call lateral moraines, there are what we call end moraines, and there are what we call terminal moraines. And you can see these moraines where we live in Ohio, if you're real careful. I know we've plowed a lot of stuff down for farming, but the topography still exists. Okay? So just to show you the max on the ice, this is the Laurentide ice sheet. There have been about 4 pulses of glaciation that have occurred in Ohio and in North America on land. About 18 that we see in the sea. But on land, because every time a new set of glaciers comes down, it kind of rubs away the remains of the last glacier that left stuff behind. So we have to be very careful looking for it. But I can tell you that I think they say maybe the ice coverage in this part of Ohio and north may be almost a mile deep at the maximum. And that wasn't that long ago. See, 15,000 years ago? Pretty amazing, right? So, you guys have heard about the Taze River. Well, it seems like the Taze River is maybe one of the most ancestral, oldest rivers in the world. And it was a vast river, okay? And you notice it started in North Carolina and flowed in what is today Illinois down into Missouri. But as the glaciers came and started to cover up those river valleys, right, with till, that stuff that's left behind, the river changed its course, and today we call it the Ohio, right? The Taze is gone, but the gorge, the river valley, is left behind, and it's buried under all that sediment from the glaciers, okay? So you can see that, you know, where this river once flowed, it's left behind aquifers and stuff, right? So like in St. Mary's, we use the Taze River as our water source. We can't use that here in Mercer County because, well, we drilled oil wells and it kind of contaminated that aquifer. So we can't really use that here. But that would have been a huge, huge river system until it got subdiverted and became the Ohio. I mean, this is what the Taze River would have looked like about 2 million years ago. And this has been running right through our backyard. No kidding. Huge river valleys, all kinds of lush plants, ice age animals and stuff. And then the glaciers came down and changed the course of the Taze River. And this is probably what it would have looked like if you were like living out here and you looked out your back window and saw that. So it wasn't really good. But as that glacier came down, it actually dammed up the Taze first, and this became something called Lake Tite. And Lake Tite was 900 feet deep, and it was huge. Over like from, you know that circle I showed you, that orange circle? Imagine making that even bigger, and that would have been Lake Tite. And it was huge, and it got dammed up. As the glaciers started to melt back, Lake Tite released all of its water. And that helped change the course of the Taze as well. So, today, because of ground penetrating radar and other studies, we've actually seen what's left of that old Taze River Valley, and it runs, look where it runs, right by New Knoxville, right by Bodkins, all the way down, and it's very, very deep, and it's full of sediments. And guess what? It also lays right on top of the Grenville fault line. Imagine that. Rivers love to flow along fault lines. And now you've got towns actually laying on top of till hundreds of feet thick. So when there's an earthquake, you really feel it because the ground is soft. This just gives you what they think the cross section actually looks like. That is a river gorge. Okay? And so when the glaciers melted, the debris and what we call till, the remains of the rocks, the sand, the sediments, the boulders, all start to fill the old Taze River Valley and simply diverted its flow. And this just shows you what the Pleistocene glaciation looked like. Now in Europe, most of Europe and Northern Asia was covered. I'm not so sure about the Southern Hemisphere. There's not as much land as you get to those higher latitudes. But Antarctica is fully, covered in ice at this point. One thing that's interesting, people think like the whole country or a whole, continent was cold, right? I can tell you this: if you were living in Florida during the Ice Age, you would have had warm days. It'd probably be more like it is, say, in Virginia today, instead of being really, really hot, right? It'd been, kind of temperate. Out to the west, we actually have a change in climate. What today is a lot of desert actually had big lakes. The remains of one is the Great Salt Lake. So as the climate changed, right, it became drier and drier in the west. Go figure. It's all desert out there, and they're always worried about, the rainfall, but they are living in the desert, and so it's dry. So I don't know what to say. People ask me questions. I don't know. I mean, I can tell you that in the 1800s, when everybody moved west, it was a wetter period of time. And everybody's like, hey, this is great. Look at all the crops we can grow, and there's water. And then that was just a couple of decades. And then back into the desert. So Okay, so Ohio, yes, we had quite an interesting fauna here. Mammoths, mastodons, giant beavers, giant bears, glyptodons, these things that look like little Volkswagen bugs covered in like bony scoots all over. Giant armadillos, giant sloths, really cool stuff. And yes, we can find some of those remains. And I don't have a whole lot of pictures here, but these are just some of the remains that come from Ohio. There's a cave bear skull, mammoth tooth, giant beaver, mastodon tooth. These are fairly common to find in the fields and the creeks. So, all right. So, as the glaciers melted back, first off, you got to remember all that ice depressed the land down. Okay? So, as the ice melts back, it takes a long time for the land to rebound up. So, we're kind of living in a low area. Plus, all that till filled in. So that sandy, kind of loose blue clay soil that we have, that started to fill in. Very poor drainage. And so we also had what's called Lake Maumee, which is the ancestral Lake Erie, which was much, much larger. And as all that started to kind of retreat back, we were left with the area we call the Great Black Swamp. And I'm not a historian, but I can tell you from what I've seen on PBS and some other stuff and what I've read, it took quite a while to build roads from this area up towards Toledo. They actually had to make them out of logs at first because the mud was so sticky. And so this was a gigantic swampy area. And this was a swampy area right here. And as you saw on the map that was presented before, you could see the watersheds all draining into this lake. And so this was a natural area to form a lake. It wasn't a lake at the time until they dammed up the rivers, changed the course, kind of made the basin, took out the trees, but it's semi-natural. It's a swamp basin, okay? So you can feel good about that when you say it's man-made. Yes, it is man-made, but it's also kind of semi-natural. That's pretty neat. So you got both. Who can argue with that, right? This map shows you the thickness of that remains of the glaciers. This is called a till map. And it shows you that where we live, the till's pretty thick. And that is the stuff that covers the Silurian down below. Some places it's 10 feet, some places it's 50 feet. Depends. Okay? Now let's jump to about 140 years ago. All right. So in Indiana, this is in like the 1860s. So they're actually digging for coal in parts of Indiana, right on the edge of what we call the Indiana gas field. And these miners, I don't know, they're opening up these mine shafts, and all of a sudden this terrible smelling gas comes out. And they think they've actually opened up the gates of hell. No, this is by newspaper stuff that I read. So they sealed it up. Well, then somebody noticed it's really cool that, some of these spots, if you poke down into it, the gas comes out and you can light it, and you got a torch at night. Well, they're actually into the commercial, or into the natural gas. And very quickly, the Industrial Revolution is ramping up in the 1800s. Well, you need petroleum to fuel that revolution. And, electricity is a newcomer in 1880, right? People used gas to light lamps and keep themselves, at night from the darkness. And so by 1886, there was a commercial gas well established in Indiana. And around, I guess maybe about 922 feet deep is where they actually found the gas veins. Okay, and so people got what they call gas fever. Everybody wanted to dig a hole and get the natural gas out. Well, this was called the Trenton gas field at first. Today it's called the Indiana and Lima gas oil field. And it was big, about 5,000 square miles, okay? And eventually, by digging down, not only did they discover gas, but they discovered petroleum. And lots of petroleum, okay? So by the 1880s, this had a profound impact on Ohio. We became, well, John D. Rockefeller had a hand here, but he actually invested money in northwestern Ohio. And we were the biggest producer of oil and gas in the world until they discovered the Texas oil fields in the 1880s, late 1880s. Okay, but oil was still going on here. In 1891, the first oil wells were drilled in Grand Lake, St. Mary's, or Grand Lake. Wood pilings were driven down for the derricks. Okay, and then by the 1910, early 1900s, even though there's still a lot of oil below our feet, a lot, it's just not economical to pull it out. So everybody moved to, say, the Texas, Oklahoma oil fields. Some stuff came from Europe. And then we were left with all these derricks. And so the state Senate actually passed a bill to provide the money to remove those old derricks and wood pilings. So by 1920s, most of that stuff was removed. Okay? Now, one of the questions is, why so much oil? Well, remember I talked about the Silurian dolomite, right? And below the Silurian in time is the Ordovician. And there's vast amounts of shale and limestone that had living things in it that eventually, because of chemical changes, became petroleum products. Now, we also live on a very faulted place because of the Grenville fault line. Those faults and fissures crack and let the oil and petroleum go upward. And it would continue to go upward, except they run into the Silurian dolomite and they're capped. And so over time, vast oil and gas fields form below the Silurian cap. And so today, yeah, you could probably go and drill for oil here. I wouldn't do it. You probably run into some problems with the EPA and the state, and it's probably not a good idea. But there is still a lot of oil. All I can tell you is, as far as the Trenton limestone, I've seen it before, but you won't see it here. You have to dig too deep, right? But sorry. I just spoiled my closer, man. Okay. So right here, right, this is an exposure in upstate New York of the Trenton limestone. Here's a little hand sample showing you all the invertebrate fossils. This is where they frack. When you hear fracking, they're fracking that Ordovician stuff a lot of times. And so we got natural fracking going on. Over time, it just released its petroleum and it moved itself up to the top. But that is the source of the oil here. It's about 1,000 feet below. And so that brings us to our present day. Okay, there it is. I got to give a shout out to Roddy. I think it's Rowdy Raider. No, we're Loudy. That's right. We had to come up with a name, so we came up with Loudy. I like it. It's kind of hodagish, but a little bit different. And probably the most distinctive things I've seen as far as sea monsters go. But yeah, so that takes us right to the very end. So thank you. Any questions?
One quick one you may have said. So how far down, as far as the oil and whatnot that would be out there, how far below the surface?
I'm thinking it's probably close to 500 to 1,000 feet, which is that's not crazy for a drill rig to drill down like that, And I think it was estimated that at least half of the petroleum remains, maybe more. But it's not economical right now to pull it up.
Okay, I have a question about the oil too. I heard that, and this could not be true at all, which is why I'm asking. I heard that like the pressure field needed to like lift the oil out of the ground was like ruined. So I heard that like if you try to extract the oil, it's hard to get it out because the pressure to make it come up is gone.
Yeah, that's true. I mean, you lose the natural pressure, right? I mean, at first you've got all that natural gas in there, right? And so that helps push the oil out. When they drill down and you see the derrick and the oil squirting out of the top, that's that pressure you're talking about at first. But then what they do, and I'm not an expert in petroleum geology, okay, but I believe they use salt water and pump it down into holes to push the oil out, which of course then contaminates the aquifers and the groundwater around there. But yeah, I mean, at first, you always see this on a movie, right? Or TV, Landman, whatever. They're digging down, they hit the oil, and but that's at first, right? But the natural gas usually comes off for quite a while, so there's a lot of pressure. Usually they burn that gas off because it's not what they really want to use. So, yeah, it just found out we could still get the oil out, but it wouldn't be economical. Any other questions?
The Grenville Fault an extension of the mid-continental rift?
No. In fact, the Grenville province is which closed up that mid-continental rift. I mean, that's what they think, right? Because it was actually a 3-part rift. and it was starting to extend northward and then to the southwest and then to the southeast, breaking at the time what we called Laurentia into 3 pieces. And you can actually see the basalts and stuff in Iowa, but you have to like get into quarries or drill down and get into the cores. But as that piece came closer and closer and closer, it pushed in against there, and we think it stopped the rifting. But yeah, we're on the Grenville right here.
Question?
Yeah.
Yeah.
Do you suggest we get earthquake insurance on our homes?
Andrea and I have contemplated this before. I mean, if you do get a 4 or 5, it could crack your foundation and your chimneys. And it's not unheard of to get that happening around here. So I'm kind of like on the fence with that, you know? That could be pretty expensive.
Is there a place where all this information we can get it?
Huh.
You just gave to us? Is it in textbooks all over the place?
Well, it's in my class on historical geology. Yeah, I mean, there's information out there. If you go to the Ohio survey, the ODNR, if you go to the geologic survey part, you'll see a lot of brochures and pamphlets documenting the different ages in Ohio. It's a really good source of information. Awesome. And the geologic survey had been gutted for a while, money-wise, but now they're putting money back into it again. And so there's actually people working there, and because I think they figured out that maybe geology is important after all. You might want to know something about the ground below your feet.
So wonder our aquifers around here aren't contaminated with oil and whatever from all of these dirts.
They are. And so the Tays aquifer, I believe, flows from like Auglaize through Mercer, and I believe that's contaminated, that portion.
What about us with wells?
Oh, you're not deep enough.
Not deep enough.
They're not deep enough. Yeah. There's aquifers are weird things, and there can be several layers of aquifers, and I doubt you're going down that deep, so it's probably fine. But yeah, I mean, I think that's one reason. I don't know how capped the wells are. I think, if they were closed down in 1910, 1920, they're not going to have the technology back then to really seal them up like they do today. I think a lot of them are just sedimented over. The lake sediment has actually just filled the wells. So one reason probably not to dredge too deep. So, but I think they have maps showing where all the extinct wells are. I think they've mapped most of them now. So, but it costs. So you can drill for oil on your property. They do it a lot in parts of Ohio. They do it all throughout Michigan. They actually have little oil wells on people's property. But then you're responsible for, when it's done, closing them off. So the oil companies, what they'll do is sell you the deed for about $1 or so, because it costs about $500,000 to close them off. And they don't want to pay for closing them off. So they unload them on people. And yeah, you'll make money for a little while, but eventually you've got to seal that well off. Unless you can sell it to somebody else. Any other questions? Yeah.
How many wells were drilled out here on the lake area?
I don't know. I would say probably somewhere in the neighborhood of 50 to 80, I would think. Judging by the pictures, it was pretty dense. So, I don't know. That's a good question. I mean, you can go to the GeoSurvey and look up the map, and it'll show you in there. I think there's some other archives and stuff. And I'm sure Steve Jackman and all, they've looked at that to see how many of those wells lay around.
State of Ohio has a map with all the oil and gas wells around the lake.
Yeah, I think, yeah. I mean, they've tried to map them as best they can, so. All right, again, thank you all.
Thank you very much.
Yeah, hey, where you walk away.